Well, thanks for the introduction. So today, what I wanted to do, and maybe we'll be able to finish it, all of it or not, is so what is the Sarkisov program? And why do we care? Okay, so my motivation of what it is and why we care starts in dimension 2, although in dimension 2, over an algebraically closed field, it doesn't give us much more than what you saw last week. Okay, but my motivation starts there anyway. So, okay. Okay, so in dimension 2, so we've seen last week a nice generating set of the Cremona group. So over algebraically closed fields, we've seen the Noether-Gastineau theorem, where P2 is generated by the automorphisms of P2 and an involution. Okay, over other fields, we can try a sort of Noether-Gastineau type of algorithm to get a generating set, but it is too complicated. We actually don't want to do it. Like if you sit down and you want to do it, you will see what I mean. You get interested in other things. And I mean, even worse, in higher dimension, we don't have a generating set. At this point, we are not quite sure, do we want one? Like a reasonable one? We can just take everyone, but that's not reasonable. And so we need to have, so this is one motivation to like get something else than the Noether-Gastineau algorithm for this theorem. And then also, if we take a general birational map of P2 and we blow up all the base points with the Sarkisov theorem that Stefan mentioned in his course, we might have to blow up at like 100 points, maybe 200 points, and we lose complete control of the surface that we get once we blew up all the base points. And we want to have better control of the surfaces that we encounter when we blow up points. Okay, so let's put some motivating questions in there. So. Okay, so as an example, I'm gonna make an example that doesn't really look an example, but it's the easiest one to do. So I'm gonna repeat the picture that you've seen all too well. That's the one of the standard quadratic map, which is x, y, z, goes to y, z, xz, and then xy. Okay, so the Zariski theorem tells us, okay, I'm gonna put the picture here. Do I have enough colors? I need 6 of them. No. Yeah, maybe. I will use green and red. I hope that's okay for everyone. Okay, we'll have a triangle here, and then the base points of this map, the 3 coordinate points. Okay, and then we blow up all of these 3 coordinate points. And then we get the hexagon. So we get the 3 exceptional divisors and the pullback of the 3 lines. Okay, purple and white are really hard to distinguish, so maybe I'm just not going to use purple. Okay, and then we contract the pullbacks of the 3 lines. Right. Okay. All right. So this is what we've already seen. And well, this is quite a nice surface. All the lines you see, they have self-intersection -1, and all the other curves in the surface have positive self-intersection. So this is a surface that we do know how to control. But we can actually we can make things simpler. Okay, we can just start with one blow up. We blow up the blue point. Okay, and then we get the exceptional divisor, and well, through this point we have a pencil of lines that passes through this point, okay. And 2 of those lines are the green one and the white one, okay, and the green one, okay, and on them we have the 2 base points. We have the red one and what used to be the purple one, but now it's the flat wrap. Maybe I'll put it in a square. Okay, and then the yellow line. Okay. So now exceptional divisors have self-intersection 1, and then the line has self-intersection -1. Sorry, the line has self-intersection 1. We blow up a point that is outside the line, so this one has self-intersection 1. And now we just do what Jeremy did last week. We blow up this point, and then contract the fiber, the white fiber. And then we blow up the red point, and we contract the green fiber. Okay, so we do so this is the picture we get. And okay, the same as the green one. and red here. Oh, sorry. Okay, I made a mistake when I blew up this point. The yellow line then passes to the red point and to the exceptional divisor. And then when I contract the fiber containing the fat point, I will get the image of the fiber is going to be here on the blue line. And the same for the green point. Okay, now in the process, the one curve will have become the -1 curve, and the blue curve will have an intersection of 1, and then we can blow down the -1 curve onto P2. Okay, so this is Jeremy last week. And these surfaces here, they all have a morphism to P1. They're Hirzebruch surfaces. This is F1, this was F naught, or P1 cross P1. And this is, again, F1. And all these surfaces, they are minimal in some sort. Here, if I contract any -1 curves, I'm going to lose any -1 curve, I'm going to lose the vibration to P1. P1 cross P1 doesn't have any contractible curves. So these are sort of minimal. So they're nicer than the surface up here, even though this one is quite simple already. And that's sort of the idea of the Sarkisov program. We want to blow up as little as possible and stay with surfaces that are like as minimal as possible, but we lose the property that every time we contract, we go back to P2. So with the Zariski theorem, we blow up a bunch of points and then we contract and we go back to P2. And during the Sarkisov program, we blow up, we go to surface, we contract, we go to another other surface, it's not P2, but it is a nice surface. We blow up, we contract, again it's not P2, but it's a nice surface, and then we can go back to P2. Okay. And again, for more complicated maps, we can look at the Jonquière maps. So they're, for me, of the form, they do nothing on the first coordinate, and then on a second coordinate, they are of the form of a Möbius map, but whose coefficients depend on x. And then what we get is a similar picture. So these maps always have a base point. So let's say this map is of degree d. Okay. Then it has a base point of degree of multiplicity t minus 1, and then it has 2d minus 2 base points of multiplicity 1. And it contracts, let's say, so we'll just, for simplicity, assume that all these 2d minus 2 base points are not on top of each other. They're all in the plane. But you can verify this formula using the Noether equations that Stefano wrote down in the last lecture. So. And I will do that. So another thing that you can check very explicitly is that it contracts the lines to the big base point. Let's say, let's give it a name. Base point P to P, and then we have base points P naught, and then P1 to P to D minus 2. So it contracts the lines through P naught and one of these. And a curve of degree D minus 1. And the curve is rational, so it has to be, it is singular, usually. It passes through these 2D minus 2 points, and it has, it is smooth in these 2D minus 2 points, but it is singular of multiplicity D minus 2 in P0. Okay, so it passes through P naught. P1 all through D minus 2. Okay. Quick question. Last week, for those who were here, did you see this? Is it new? Not quite clear. Okay. Well, I hope you remember something from my lecture. Okay, so this is the okay. I'm not going to prove it, but you can check that these things hold up with the equations, with the Noether equations from the last talk. And then for the third one, a sort of intuition for like general birational maps of P2 is that if you have a point let's say this is F. If you have a base point of multiplicity M, then there is some curve here of degree M that is contracted onto this point. So this is for general maps, this is true. For maps with base points that live on top of each other, it is not true anymore, but that's sort of the general gist. And for this, the inverse of this map is of the same form, only you replace A, B, C, D by the coefficients of the inverse, so D minus B minus C, A. And so it will have the same form, it will have the same multiplicities, and so, exactly, so you can know what are, so okay, you have a point of multiplicity D minus 1, some points of multiplicity 1, and then because of the first 2 points, you know that there are, what are the curves contracted onto these points. So that's the idea, the intuition for the idea to show that. Okay, so let me redo the picture. Here. So I have now less colors. Yes, yes. I think I'm not going to use a lot more colors, but thanks a lot. Awesome. Well, let me check how many colors I used in my picture. No, that's actually fine. Okay. So I have the point P0, and then the points P1 up to P2 and up to P2D minus 2. Then in white, the lines through P0 and the Pi. Okay. And then in yellow, the curve of degree P minus 2 passing through P0, degree minus 1, sorry, that has a multiplicity of d minus 2 here. Now, Zariski theorem says we can just blow up all these points and we'll find curves to contract and go back to P2. But it will be, so if D is very large, we'll blow up a lot of points, and then the surface we obtain will be complicated, and it will be hard to figure out, it might be hard to figure out what are the -1 curves on this surface that we want to contract. So instead, what we want to do is we blow up P0. We get to the surface F1, right, that has the exceptional divisor of P0 as a -1 curve. And then the lines through the PIs. And, well, somewhere, so we have the yellow curve that passes through the green points. And then if the singularity is very agreeable, we have some sort of wiggly line here. And now what we do is we just blow up these points one after the other. Okay, so we blow up P1 and then contract the line passing through P1. So the line P1. Okay, and then we blow up P2 and then we contract the line through P2 and so on. And it turns out, so if you follow Jeremy's algorithm, you can compute that we get to a surface. Oh, okay. So we still have, that looks like this. And then it will turn out that the yellow curve has become a -1 curve. The red curve will have become something of self-intersection -1 squared. And we can contract the yellow curve and get back to P1. P2, sorry. Okay, so this is a sort of generalized decomposition of this example, and we have what we did is that we decomposed the Jonquière map into small birational maps that are very controllable. Each of the surfaces appearing here is a Hirzebruch surfaces, we merely blow up one point, contract one fiber, and then we get to the next surface. So things are easier, but we give up of staying in P2. We do go to different surfaces. Oh. Okay, that took longer than I anticipated. Okay. So what we've seen is exactly the Sarkisov program in dimension 2 over a closed field. So and that is so the theorem that is by Sarkisov in 96 and by Gorty in 95. And then you saw a sort of version by Jeremy last week. I'm going to write the theorem and then I'm going to make the definitions, okay? So any partial map of P2 can be decomposed into Sarkisov links. Oh, yes, thank you. Yeah, so both Iskovsky and Gorty were inspired by Sarkisov, who gave the idea of this type of program in a lecture in the 80s, in the early 19s, I think, but he did not precise it. So both of them came out with the same version, very close to each other. Okay, and maybe. So, what are the Sarkisov links? Wait, I'm not finished. If K is algebraically closed. Okay. So the Sarkisov links we have is we blow up P2 in a point. And we're going to say that F2 is the blow up of one point. It is a special surface, and it has a fibration over P1. Okay? So this is a link of type 1. And we have links from one Hirzebruch surface to another Hirzebruch surface. And they preserve the fibration. These are links of type 2. So both these blow up one point. And then for symmetry reasons, we have the inverse. So actually the link of type 1 is a birational map. Then we have the contraction. So we go from F1 to P2. And then we have a final one that is type 4. We exchange the fibrations of P1 cross P1. So this is the first projection, and this is the second projection. And basically, this version of the Sarkisov program follows from the Noether-Castelnuovo theorem and what Jeremy did last week. So you can write any birational map of P2 over an algebraically closed field as a composition of the standard transformation and automorphisms. Plus automorphisms. And then sigma you can decompose into these links, as we see, and you're finished with the. And so sigma can compose into these links, and that sort of finishes the idea of this version of the theorem. So you see that, okay, my motivation is now half an hour. In dimension 2 of an algebraically closed field, the Sarkisov program doesn't give us a lot more than we know from the Noether-Castelnuovo theorem. There are still some things that you can prove maybe in an easier way than using the Noether-Castelnuovo theorem, but in general, basically it doesn't give so much new things. However, if we are interested in a higher dimension, in the Cremona group in higher dimension, or in the Cremona group over other fields, the Sarkisov program gives us a lot more. It sort of replaces the idea of a generating set for that group. Do you have any questions up to here? That he gave this. Oh, really? That early already? Okay. So it was in the 50s, 60s, in the 80s. I'm sorry. Okay. I was not aware of his age. Okay. Thanks a lot for the. Yeah. Okay. So I'll write this down. So this is after idea of Sarkisov. Okay. So now we want to have a version over non-closed fields. Why? So if you are already interested in algebraic birational geometry over non-closed fields, this is not a question for you here, you know. But for everyone else, so what happens in dimension 2 over non-closed fields sort of gives you an intuition what happens in dimension 3 and higher over closed fields. So imagine you have some sort of vibration, x, from x to b. Okay. And some sort of vibration. Let's say it has like connected fibers. Good things, anyway. And then, so X, the generic fiber, is a variety, X over the function field of B. And now if you want to do some birational geometry that preserves the vibration, it comes down to doing birational geometry on this variety, which is not over a closed field. So you're kind of interested in knowing if this is a surface, in knowing birational geometry over a surface over an unclosed field. Now, if your field K is of characteristic 0, you're lucky. This is of characteristic 0 as well, and your life can be nice. If your field is of positive characteristic, this field is not very friendly, and then things get more complicated. So depending on the characteristic you work in, you, this changes a bit on what you want from your surface case, maybe. So this is in as a different motivation. Yes. Mm-hmm. Mm-hmm. Yes, but only a Sarkisov version that preserves the vibration. So, so you'll have Sarkisov links, and every threefold you get will have a vibration over B. You get a relative Sarkisov program. So the motivation serves you for things that preserve the vibration. Yeah. Yeah, exactly. Yeah, exactly. So if you have a birational map that does not preserve the vibration, that maybe goes to a birational map from X to Y, and Y does not have any vibrations at all, then the Sarkisov program of the generic fiber doesn't give you a Sarkisov decomposition of this birational map. You need to have more. Something like that, exactly, yeah. Okay. So for the purpose of the lecture, I will, at least for the moment, I will stay with certain types of non-closed fields, and those are called perfect fields. Because the imperfect fields are even, perfect fields are nice. I'm going to tell you why. And then imperfect fields, they are a lot less nice things. If you're used to working over smooth surfaces and you work over imperfect fields, you will, your intuition will give you nothing. But over perfect fields, you can carry over your intuition from working over an algebraically closed field. Okay, so for now, okay, be a perfect field. So, for instance, these are all, this is when the characteristic is 0, or if K is finite. Okay. And the definition is, so here, if you have an algebraic, a finite extension of fields, so then any polynomial P in L of T, in L of K, sorry. Okay, now I'm gonna write it differently. Okay. K is separable. So K bar, the algebraic closure or an algebraic closure. Any algebraic closure is separable over K. That means so if P is a polynomial in K that is irreducible, then P has only simple roots in K bar. So for instance, not perfect is F2 of t or Fp of t, because x to the power of t minus t, this is irreducible. But it factorizes as a p power. Sorry, p. Sorry, I need to make a p here. It's sorry, messing up things. I will keep. No. Okay, now I'm better. Okay, so not perfect. For instance, we take this polynomial x to the power of p minus t over this field. Over the algebraic closure, we can write it as something to the power of p. So it has only one root. Okay, so this is not. Sorry, somebody asked the question and I missed it. X here. Sorry. No, it was okay. Okay. I heard Hirzebruch. I was confused. Okay. So for these. So if we work on surfaces over these smooth surfaces over these fields, things are nice because basically here the Galois group, Galois theory makes sense. So the classical theory makes sense. Okay. And then whatever you know how to do over an algebraic closed field, you can do the same over a perfect field by just doing it equivariant with respect to the Galois group. Okay, so for us, a smooth surface over the field K. Again, this is perfect. So this is actually, so when I say that, what you have to imagine is that I look at X over the algebraic closure of K. So this is X, and I tensorize with spec of K bar over spec of K. And then together with the total Galois group, with an action of the total Galois group, of K bar over K. And the action has a specific property. It says that the orbits of any point, the orbit of any point is finite, and the orbit of any curve is finite. So there is a bijection by Borel-Serre that says if X is quasi-projective, these are really the same as quasi-projective surfaces over K. So okay, so let's say maybe smooth. So Borel Serre. And the bijection is from X, we just tensorize with back K, and then we get naturally the the action of the Galois group. And in the other way, we take X, K bar, and then we quotient by the action of the Galois group. And the fact that our orbits are finite will actually give us that the quotient is again a variety. Okay. So in our case, these are really the same. And I'm going to make an example. So, okay, we have E2R, okay? So this is, for us, the same as E2 over C plus action of the Galois group of C2 over R. That's just lemma 2 by, so let's say this is generated, this is by, yeah, let's say this is maybe tau, okay, and tau acts by complex conjugation. So very intuitive. Now, maybe more interesting example is P1R, or P1. What kind of, so what kind of actions can we put on P1C that give us R curve? So either we can act like here, just by complex conjugation on each of the factors. Or we can also exchange the two factors. And here, what you get is what we write P1R. Okay, that's just the projective line over R. And here, what you get is something else. Why? So here, I can compute the points fixed by this involution. These are the real points. So and these are that UV, U bar V is V bar U. Okay, and you can show this is now the second one, the set of real points is the set of UVs, again, that are fixed under this involution, and that gives us minus V bar V equal to U bar U. Okay. This is always positive, this is always negative. And 0, 0 is not in here, so this has no real points. Okay, so for a given variety over Z, and the given action and the Galois group, I can put different types of structures on my complex variety of real structures. So actually, the exercise I can give you is that the second example is isomorphic to the conic x squared plus y squared plus z squared to 0. Am I right? No. Oh no. No. Okay. Was it okay? Yeah. In P2 over R. So is R isomorphic as R variety? So here, isomorphic as for R variety. This means in our language here, the one that I chose for this course is that we have an isomorphism from P1 C to this conic. And we have here the action of 2z uv goes to minus v bar and u bar. And here, this conic is sitting in P2R. So as by that I mean it is a subvariety of P2C and it is invariant under this action. Okay, so here we have the action xyz goes to x bar, y bar, z bar. And being isomorphic, so this is just an isomorphism as Z varieties. Isomorphic as R varieties would mean that if I apply, right, so that everything commutes. So if I apply first the group action and then the isomorphism, I get this group action. So maybe. Okay. And okay, so regarding forms, so there is a sort of equivalence between, in general, if you have a rational variety and you have a formula, sorry. So, okay, you have a variety over a field, let's say R or something, or like a finite field. And over the algebraic closure of the field, this variety is rational. It can be very hard to figure out whether the initial variety over K was rational as well. So there are lots of people who do research in that direction. And also, if you are given, let's say, a variety over C, it can be very hard to know how many real forms this variety has in general. So there's some types of varieties where we know how many forms we have and some where we don't. Okay. So okay, so for the last 5 minutes, I'm just going to write down the version of the theorem from before. Sorry, why did I? Okay. Skovsky. Gotti. Now, our Sarkisov links will look a bit more diverse than the ones we have over algebraically closed fields. So first, we have the ones that are over there. So we have a surface, X, where we blow up one point. And remember, one point over a closed, perfect field, this is an orbit, a Galois orbit of points over the closure of the algebraic closure. Okay. We blow up one point, and then we get to a different surface. And the next surface is supposed to have a fibration over P1. Okay, this is a conic fibration. And X is supposed to be a Pezzo surface. So this is a link of type 1. And then links of type 2, there are two types. So we go from a surface, we blow up, the diagram looks the same as links of type 2 between Hirzebruch surfaces. We blow up, we have a fibration over a base, we blow up, we contract something, and we do all of this over the base. Now here there are two options. So P is P1, and then in that case, X and Y are conic bundles, or conic fibrations over P. Or the option B is that B is a point, and then X and Y need to be the Pezzo surfaces. And I'm realizing that I forgot conditions. I will add them right away. Then type 3 is just the opposite. So actually the link is the birational map going to the top, and then we have contraction of a Galois orbit of -1 curves. And in order to contract an orbit of -1 curves, they need to be 2 by 2 disjoint. Sorry. And then finally, so this is the type 3, and then we have type 4. It's the exchange of 2 fibrations. So two fibrations. Then I suppose. Conic vibration, and this is a conic vibration. Okay. So what I need to add is that all the surfaces, they are smooth, so I'm not contracting any -2 curves or anything. And if the variety where I start is at the Pezzo surface, so here it should have pica rank 1. So it should be minimal. There should be no orbit of -1 curves that I can contract. And so surfaces. Here, yeah, that's okay. Vibrations. And here, where I wrote conic vibrations, the pica rank should be 2. So here, pica rank of y1, and here. Okay, so this is very, very fast, an overview, and I will sort of continue. So next time, tomorrow morning, I will sort of continue here, and then we slowly go over the Sarkisov links again, and then we'll continue. Yeah, that's it for today.
A birational map is decomposes into Sarkisov links and isomorphisms. And the fourth link is an isomorphism. So why do we have this?
Yes. Okay. Also here, isomorphisms. So, because a priori, so if you take a link of type 2, I can apply an isomorphism of this surface that induces the identity on P1, and it will still be a Sarkisov link. But so it's a bit a matter of taste. We have had this discussion a lot of times. I've had this discussion a lot of times with my collaborators. Let's say I have a map from. Okay, so first of all, I mean, not all automorphisms of P2 or of these surfaces are of this form, right? So you kind of have to include in the theorem what P2 somehow. Yeah. Okay. And then links are only defined up to automorphism. If I add an automorphism, I will still have a link. And if I want to, I could add like maybe an automorphism here, and an automorphism here that commute. And then I have a diagram that is not technically the one I gave because it does something on P1. So I have to include this in the generating set as well. And then, yeah, so, yeah, this is the reason.
Thank
Okay.
you.
The right answer is you don't think of surfaces, you think of fiber surfaces.
Yeah, I
Projection. And then they become non-isomorphic if you have
Okay.
projections which are completely
Thank you.
well. So, sorry, maybe I'll repeat the naive answer because in this Sarkisov business you don't think of surfaces by themselves but together with the fibration. And if you have two different fibrations, my intuition tells me that the links should be different. If the fibrations are not conjugated by automorphism. Okay. So
Yeah.
maybe that's another
Yeah,
way
that's
to
actually-
phrase your
yes.
answer. Okay.
That's
Not-
actually- yeah.
nothing more.
Yeah.
Okay.
Yeah, you're right.
Well.
For instance, if you take X to be P2 blown up at 9 points which are the base points of the cubic points, then the book of automorphism is large. And they are not coming from automorphisms from P2, okay? They are not coming from P2. These automorphisms, we want to decompose them in this. We don't want to say, oh, there are automorphisms that don't care. This is because when you do that, the surface is not a surface which is taken as a modified space. The automorphism is not. But you need to have something.
Okay. Thank you. And I will add this here too. So isomorphisms of the Pezzo. I learned it's a big D. Okay. So the way I want to go ahead tomorrow is that, so I wrote down these two theorems for P2, but they hold for a larger class of surfaces, and then I will sort of try to unify the things that I used here, and then we will see exactly what Serge meant, and Michel also by like a surface plus a structure. It is really, yeah.
Okay, very good. So, further.
I'm getting older, so I cannot do everything. So the base, when the base is P1, it's P1 over K. It's
Yes.
a real form of P1.
Yeah, it's
No,
P1 over
it's
K.
a true
Because I assume that my birational maps are between P2 and itself. Otherwise, you're right. Could be anything.
Yes.
Yeah, they are rational. Yeah,
They're
here.
rational over K, so if you have an image curve, it's P1 by common sense. Okay.
Yes.
Yes.
So. Yes. Yeah.
Any further question or comment? Okay, well, thanks again.